Department of Physics, IIT Kharagpur. Mr. Kannabiran has interest in out-of-equilibrium systems, specifically turbulent flows, magnetohydrodynamics, and stochastic systems. He has done his PhD from École Normale Supérieure Paris, working on turbulent rotating dynamos, and subsequently went for a postdoc in oceanography at CA Saclay. So today we are going to hear from him transitions in turbulent flows and extreme events. Over to you.
Thank you, Anubhav, for this very kind introduction, and thank you all for coming. So today I'll be I'm Kannabiran Seshasayanan from the Department of Physics at IIT Kharagpur. So I'll be talking about transitions in turbulent flows and extreme events. So why am I interested in transition to turbulent flows? Before I go into the topic, a few very pertinent examples in this particular genre would invite you to start looking at this particular set of processes in more detail. So one of the most famous transitions between turbulent flows occurs in flow path cylinder. You have a bluff body. So here's the drag coefficient as a function of Reynolds number. We know that as the Reynolds number increases, the amount of turbulence increases, and the drag coefficient goes to a viscosity independent scaling. Right? And now, beyond a particular Reynolds number, we know that there's a sudden crisis which is related to the boundary layers associated close to the bluff body that is put here. And this drag crisis shows that the CD suddenly drops and then again goes to a viscosity independent run. Right? So here you have a transition from one form of turbulent flow to another form of turbulent flow, and there's a transition between these two turbulent states. Right? And then here I show the transition from zonal flows to block flow. So in the upper atmosphere, so you have these zonal jets which are circulating, and because of this anticyclonic vortices from time to time, they might block the zonal flow, and you will have a reduced throughput or reduced flow rate, which can occur in an intermittent manner, or it can occur can just lead to a blocked state. Right? And then there were some experiments also which repeated such kind of observations. And going on to more the magnetohydrodynamic part. So here's an experiment which is known as the DKS dynamo experiment done at Cadarache in France, where they had a liquid sodium put between two counter-rotating discs, and beyond a particular Reynolds number, here the control parameter is the magnetic Reynolds number. So beyond a particular value of the control parameter, they observed exponential growth of magnetic fields. So already there's a transition. So this is usually done at very large Reynolds numbers, typically of the order of 10 to the power 5, 10 to the power 6. So already you have a transition from a hydrodynamic flow to a system which is governed by emission equations. And even beyond that, if you were playing with the symmetries, they could also observe this onset of this reversals of the magnetic field. So one could also see transitions from a state where the magnetic field was not reversing to a state where the magnetic field starts to reverse. Again, another example among transitions between turbulent states. Right? And finally, some experiments where people have conducted 2D turbulence in a thin flat geometry, between confined geometry, forced 2D turbulence, forcing which is done magnetically. And what they observed is that at some particular values of the Reynolds numbers, one could get these small vortices, which later on led to some what is known as this negative viscosity instability, creating these large-scale structures. And beyond, so by controlling the large-scale friction, another control parameter, they could see the spontaneous reversal of large-scale structures. So again, another transition from a state where you had a large-scale condensate and a state where the large-scale condensate reverses directions. So these are some examples where the turbulent flow itself transitions between different states. Now, the kind of terms that we look at are fall under a slightly different category, where we observe that the transitions are critical. In a sense, here the transition is occurring due to a change in the direction of cascade. So if we take the problem of three-dimensional turbulence, so as we reduce the height of the box, the three-dimensional setup, the system goes to more and more two-dimensional system. And by just changing the geometry of the problem, one can change the direction in which energy cascades. And one can go to a large-scale flow structure just by making the box size as small as possible. And it can occur to many different states. So if you have a order parameter which measures the flux, let's say going to large scales, and the x-axis, let's say it's a control parameter, let's say the typical height, one can go through some different possible ways of transition from one state to another. And depending on the kind of problem that one looks at, so thin layer turbulence, or rotating stratified turbulence, where the Rossby number becomes the critical control parameter, or MHD turbulence, where you have mean magnetic field, similar kind of behaviors are observed. And so here also you have a state where the system transitions from one form of turbulence to another in the presence of an external control parameter. And not just the fact that there's transition, we also observe certain kind of anomalous exponents in many of these systems. So here I show the transition from 2D turbulence to 3D turbulence. Also a state, along with it, I also show the transition from a hydrodynamic system to an MHD system, which occurs through what is known as the dynamo effect. And on the y-axis, I show the first moment. The first moment, let's say, is the magnetic field. We go from a state where B is 0 to a state B non-zero. And I look at the first moment, and the x-axis is just the control parameter over the critical value. Right? So beyond the critical point, the magnetic field goes exponentially and it saturates. And the first moment, in what we expect from mean field theory, is that the first moment should scale like the distance to the threshold to the power half. And the second moment scales like the distance to the threshold. The third moment scales like 3 by 2 and so on. The nth moment scales like n by 2. And what we find is that the first moment itself scales like the distance to the threshold to the power 1.14. So it's an anomalous exponent. So this we observed in some very large aspect ratio systems where we have forced 2D turbulence and then forced 2D or 3D turbulence, and then we looked at onset of magnetic fields or onset of 3D perturbations. So independent of the problem that one looks at, we could actually observe such kind of anomalous exponents. So the transition between turbulent states can go to critical transitions, also can give you some anomalous exponents. Right? So a lot of things which are not well understood, and this will be the kind of problems that I'll be looking at. So to go into detail, I'll start with what is known as rotating flows. So I'll be linking these transitions to what is known as extreme events. So I'll take this toy problem of rotating flows, and then I'll show how extreme events are actually occurring in this problem, why are they related to this problem, and then we'll study about these extreme events. So for that, I start with the toy problem of rotating flows. So rotating flows you can observe in nature. So Earth is rotating, many stars are rotating. Yeah.
So in previous slide, the shape of messages, the transition in your case, let's say it's like a critical transition, but with an anomalous expansion.
Oh, no, not for all MHD, or not for all dynamo effect. So it depends on a certain kind of geometry. We do observe certain anomalous exponents. Right? If the aspect ratios are very large, we observe such kind of anomalous exponents. Whereas in, let's say in the VKS experiment, if I remember correctly, they also had the first moment also was scaling with, so it didn't give the exact half power down. It's not, so the turbulence has the effect of noise is there on the exponent. In many cases, we did observe half. If the aspect ratio of the system is more close to 1, we did observe the standard mean field theory, even on the turbulent system. But if one increases the scale separation between the box and this typical size of this vortices, right, there is an anomalous exponent which occurs.
That data is not here.
Oh, the other one is I haven't presented, but I can show it later. So there are ways. I mean, there are cases where you get the mean field theory, but there are systems where you do not get the mean field theory. So there are a lot of open questions in why do we observe this, right? And then there's also this particular problem, for example, can be mapped to some multiplicator noise phase transition kind of field equation, and that also shows some similar exponents. So yeah, so in certain in the scale separated systems, this is what is being observed. Whereas if you do not look into scale separation, you can also get to the mean field theory, where all the moments scale like n by 2. in some of the dynamo experiments, they could get the mean field theory. It's only when the turbulent fluctuations are very strong, so some deviations have been observed. Okay, so looking at rotating flows as a simple example to study such kind of transitions. So we know that if we take, let's say, take a rotating tank and then we look at some perturbations, you just disturb the fluid, we can quickly observe that they start forming this large scale condensates if it is rotating fast enough. So basically what one sees is that there's an invariance along the axis of rotation which comes in due to the Taylor-Proudman theorem. So the vortices become invariant along the axis of rotation, and you have, let's say, either co-rotating vortex or contra-rotating vortex moving. And this can be shown exactly. So if you look at very fast rotating systems, my postdoc advisor, Basically, has shown that beyond a particular rotation rate, all kinds of perturbations are not forced, they decay exponentially. Right? And this is because you have the exact two-dimensionalization. Even in the turbulent regime, the system becomes exactly two-dimensional. So the question that we then ask is, can we try to study the transition from this exact two-dimensional rotating flow to a three-dimensional rotating flow? So one can, because of this exact two-dimensionalization, one can look at perturbations of this 2D background, 2D rotating background, and we are interested in finding out the domain where the system becomes two-dimensional and when does it start becoming three-dimensional. So let's say you take a system which is very fast rotating, and then you look at perturbations. How do they evolve? When do they start becoming unstable? Right? When do they start becoming three-dimensional? We know that if you don't rotate the system, then it becomes three-dimensional. And for very fast rotating systems, you expect it to be two-dimensional. Right? So again, one can do this linear stability analysis, just that the underlying state is turbulent. And we observe, so this is the threshold between Reynolds and Rossby. And depending on the box size, there's a transition from this 2D turbulence to 3D turbulence. And basically, there are some two different scaling laws. So the red curve corresponds to an aspect ratio, the height and length is order 1. And the blue curve is height is 10 times smaller than the length. And so depending on the aspect ratio, you have to, it's either more difficult or less difficult to maintain the system to that. Right? And the green curve is an aspect ratio in between. So in the limit of large Reynolds number, there are two different scaling laws. One is Reynolds going like Rossby to the power -1, transition from between these two states. And for the blue curve, it goes to a state where Reynolds is, or the Rossby critical is independent of the Reynolds number. I think this is the Rossby critical. So the question then is, can we understand this scaling and what triggers this transition? So one of the first mechanisms that basically triggers this transition is what is known as the centrifugal instability. So in the rotating system, I showed there are two different large-scale vortices. This is some simulation of rotating flows where you have this positive and negative vortex. What happens in one of this instability mechanism is that the contra-rotating vortex, or the vortex which is rotating in the opposite direction to global rotation, its rotation rate exactly matches the global rotation, and there's a three-dimensional instability which starts getting triggered. This is given by the Rayleigh factor. The rotation and the rotation rate of the anti-rotating, contra-rotating vortex becomes comparable with the global rotation, and the system no longer feels any rotational effects. So you have an instability which makes the system three-dimensional. Remember, the vorticity of the underlying 2D flow is turbulent. Right? So you have a system which is fluctuating in time. So the threshold you can do by doing some kind of bounds. So we know that the minimum of the vorticity, the time average value can be bounded by a value which is proportional to u over there. Yeah. From 2D turbulence, one can write this down because we have inverse energy cascade. It can be nicely bounded from above by quantity which is proportional to u over there. And this leads to a threshold where Rossby becomes constant. The other is when you have parametric excitation of waves, because the underlying flow is turbulent and it's oscillating. So these oscillating underlying flow or fluctuating underlying flow can excite inertial waves, which propagate into the flow. rotating flows are one kind of systems where you have bulk rays which propagate into the fluid, and because of this underlying fluctuations, you have waves which are generated, and some of these waves gets destabilized, and it's a parametric excitation by the underlying turbulent flow. So we see that such kind of similar excitation of waves also observed by just oscillating flows. Okay? And one can again find some threshold which is some loss beta and some loss which is constant. So more than the scaling loss, I just wanted to say that there are two different mechanisms for instability. One is related to these places where the vorticity becomes small enough that it's comparable with the global rotation in the negative sense. So what we see is that whenever the vorticity becomes very negative, you have an instability which gets triggered. And for the parametric excitation, what we find is that the places where the strain rate of strain tensor, so by measuring what is known as the determinant of the rate of strain tensor, I'll define it properly in a bit. So just think of it as some kind of a measure of the strain. What we find is that so here I show some temporal evolution of the underlying vorticity, the perturbation that is going on top of the vorticity, the kinetic energy of the vortice of the three-dimensional perturbation, which is going through this non-monotonous growth because of the underlying fluctuations, and you have this strain rate determinant which is set here. So what I want to point you towards is that blue kind of minimum value of the strain rate determinant. What we find is that whenever the blue patch where you have the rate of the strain determinant is very minimum, you have an instability which grows exponentially. In other instances, that it starts to decay. So there's that correlation. There's also correlation between this minimum of the strain rate determinant and the growth rate of the three-dimensional perturbations. So this strain rate determinant can be present on top of both the positive or the negative vortex. It doesn't matter. And the strong shear regions near the vortices can trigger this parametric excitation of these. And in the turbulent flow, there's a direct correlation between growth rate and this minimal value of the strain rate determinant. So what we see, yes? Yeah? So in a sense, it's becoming independent of the viscosity. So if we change the Reynolds number, we should no longer see any effect of viscosity. So so it's very intermittent. Right? So the signal is very. Yeah. So in certain instances, it becomes like quasi three-dimensional. At certain instances, the 2D modes are stable. At certain instances, three-dimensional. So it's a very intermittent signal. So that is what one observes whenever you are in the very large Reynolds number regime, like the video that I showed here, which is the growth of this three-dimensional perturbations. So this is a log as a function of time. So positive slope means it's growing, negative slope is decaying. So from time to time you have positive slope where you have three-dimensional perturbations growing, and some other times you have three-dimensional perturbations decaying. Variance seems to go down. Oh, that variance is just that is just a value that we put in order to, because we're not exactly sure where the threshold is. So the endpoints of the variance are just points where we are sure that it's decaying or we are sure it's growing. So it's something which we have defined it like that. There will be an exact threshold depending on how long you integrate. So this is an exact transition problem which we haven't studied in detail, but we know that there's a transition. Oh, even in a sense. So here we have the underlying 2D vorticity, right? And here we have the three-dimensional which are going on top of the 2D vorticity. Right? And this is the energy, the log of the three-dimensional energy as a function of time. And here I find what is the strain, the determinant of the strain rate tensor for this particular field. So you have some perturbations which are going on top of the 2D flow, right? And what I'm trying to tell is that whenever this 3D perturbation sits on top of this strong strain regions, basically the minimum of the strain rate determinant. So whenever there's a spatial correlation, let's say, between these two fields, you have a growth of the unstable mode. So the if it's positive, it's growing. So it's not. It's a linear problem. It's always growing or decaying. No, it's log, so it goes to minus infinity. So it's like if you have a stable, if you have a flow which is kind of time independent, you expect either exponentially growing or exponentially decaying modes. Here the underlying flow is fluctuating, so the growth itself is intermittent. So gamma itself does some kind of a Brownian motion, let's say. I mean, not Brownian motion, but it's a noisy signal. So you have. So what I want to say is that if you just follow the video. So whenever you have this strong strain rate region, which is the instability sitting on top of the strong strain rate region, you have this growth of these perturbations. And from time to time, when it's no longer this blue curve is no longer sitting on top of it, you can also there's a spatial decorrelation. Then there's a decay of this perturbation. And again, when there is a spatial correlation, let's say, we again start to move. And we have done some analysis of course, different points of correlation of this minimal determinant along with the growth rates. And what we find is that whenever the minimum values of the strain rate determinant goes below a particular value as a function of the rotation rate, we get. And similarly, for the centrifugal instability, when the counter-rotating vortex, the vorticity of it is below some typical value defined by the global rotation rate, you have this onset of this centrifugal instability. So in both these cases, there's some kind of a large fluctuation which triggers certain kind of these transitions. With very large negative values, which kind of triggers these transitions. So I forgot whether I answered your question.
Yeah. What the blue line is again? What is it?
Oh, just a smaller box.
So that's a large aspect ratio.
Yeah, H
large
level is,
horizontal to
yeah,
vertical.
yeah, exactly.
And so I'm curious, how do you? So this means that even at Rossby number order 0.1, we can still see a transition to 3D.
This is for like laminar flows. So laminar flows, you can just do more or less Rayleigh criterion should give you the answer. So very low values of Reynolds numbers is a kind of quasi-laminar. It's only the large Reynolds number I'm interested in.
Yeah, so the large Reynolds number, even at order 0.1 Rossby number, you can get a transition to 3D turbulence.
0.0, yeah, 0.02, I guess. Yeah. So it depends on how we define the Rossby number. What is the length scale that we use?
I'm just wondering how you would reconcile this with what is seen in the ocean and atmosphere, where at 0.1 Rossby number you see basically positive traffic dynamics, right?
Yeah, so in a sense, so there you have stratified systems, so you do not have this exact two-dimensionalization. Be slightly careful about extending the direct observations. So in a purely rotating flow, there's a 2D attractor which exists for very low values of Rossby. Whereas for rotating stratified flows, this is not the case. So this is something to do with this frequency gap. Inertial gravity waves have frequencies from F to N. So yeah, so you will always have some form of 3D perturbations always present, even at very low values. This is since rotating structure. Yeah. So I'm just talking about rotating flows.
In rotating flows, typically the 0.1 Rossby number, it's all this quasi-geometric.
Yeah, so but there will be some perturbations, some waves which might not decay. But here is like all.
So here, what are those waves? What are those particular?
So here you have this parametric excitation, for example, inertial waves which can be excited.
Due to what?
Due to the underlying oscillations or fluctuations of the underlying. So let's say you take some sinusoidal velocities of L and just oscillate it in that. Like
So this is being perturbed. The system.
So the underlying flow is turbulent. the 2D flow is kind of turbulent. So this is what I showed here. The underlying flow, the two-dimensional flow is kind of turbulent. The columnar vortices are moving on in a turbulent manner. So this random convection diffusion of this columnar vortices can lead to this parametric excitation. Yeah. Okay. So just continue. So basically, I'm interested in this. To not understand this intermittent growth, and also to try to understand when does this exact onset occur. We are interested in trying to understand where the minimal, what are the statistics of this minimum of the vorticity and minimum of the strain rate tensor, right? Because these are the ones which trigger either the centrifugal instability mechanism or the parametric instability mechanism, right? So what are the distributions of these quantities? So before I go into that, just a bit brief D2 to get ourselves equipped with some basics of extreme value statistics, which a lot of people in the statistical physics community have understood. So if we take n, so just a recap basically for people who have already done this. For people who haven't seen it, maybe I'll just try to introduce you briefly what. So if you have n random variables, identically distributed independent random variables, and you're looking at extreme values of these variables. So one can show that this falls under three of the main classes of distribution, which are known as Gumbel, Fisher, and variable. And this falls, it's a mathematical theorem which can be proved. And this theorem is called the Fisher-Tippett and Nedenkoth theorem. I don't know if I'm pronouncing the name correct. So one can show that depending on the distribution of these independent identical variables, right? So one can show that the limiting value of this distribution of the extremes of this n random independent variables, extrema of them, it falls into one of the three classes of distribution, right? And there are a bunch of articles historically which started with, and extreme value statistics is a field by itself. Many people work on it. They try to apply such kind of distributions to many different fields, right? But one should be careful that this is a problem where the random variables are independent and identically distributed. Okay, so just for people who haven't seen it before, just a quick slide on just to show how one can get into some kind of a distribution. I'm just taking the Gumbel distribution, which is the most, let's say, kind of famous distribution among the three. We take n independent Gaussian variables, so variables with exponential or Gaussian tails, let's say. Here I'm taking Gaussian tails with zero mean and let's say standard deviation sigma. Let's say we have some 10 different variables n different variables x1, x2 up to xn, and we are looking at the maxima of these n variables, right? And we are asking what distribution does it follow, right? So you can say that, okay, let's say the first variable has reached the maxima and all other variables are less than this maxima. This could be one situation. Or maybe the second variable has hit the maxima and all other variables are less than the maxima, and so on, until you hit the last one, where the last one hits the maxima and all other variables are less than the maxima. Right? And because these are independent and identical distributions, you can easily solve this equation, and you get the maxima to be this exponential times this Gaussian times this modified error function. Yes. And the large n limit, it asymptotes to what is known as the Gumbel distribution. So here, in the large n limit, it goes to some exponential minus s, and s is just a rescaled value of this x max, rescaled with a particular mean and some other mean and sigma, which scales with some capital N in a particular way. Or you can do this in many different ways. So one particular way. So this is what the theorem states. Like if you have Gaussian or let's say power law tails, exponential tails, one can show that the distribution of extremes falls into the Gumbel distribution. And for power law tails and others, you can look into Fisher and variable. So this is for random, identical and independent variables. So let's now look at what happens in the case of turbulence. So I just remind you that why are we looking at it? Is to look at to predict when do these turbulent transitions occur, at least in the context of rotating flows. We see that there's an onset whenever the vorticity minima or the rate of strain tensor becomes very less, right? So what we do is to look at the two-dimensional turbulent solution forced by a typical forcing, which is body force turbulence. So we take some typical Kolmogorov type forcing, which is an incompressible fluid, and we look at extreme values of the vorticity and the rate of strain rate tensor. So rate of strain, it's a tensor, it has 4 quantities. So one has to worry about the rotations and how does the tensor vary with rotations. So there are 2 invariants in 2 dimensions of the rotation of this tensor. One is the base and another one is the determinant. So these are invariant quantities of the rotations. So kind of how we define the axis. So by looking at the trace is 0 by real incompressibility, and the determinant is the quantity which is what. And previously, I also showed the correlation between the growth rates and the determinant of this strain rate. So it's defined in this manner, and we are looking at what is the minimum value of these fields over the whole space. Right? And by understanding this particular distribution, hopefully we try to understand the distribution of these growth rates, or distribution of this intermittent phenomena, where you have this transition from one turbulent state to another. dux minus duy. dx. Yeah, maybe dux minus dvy. You can write it as minus of dvy. Can be written as minus of dux by incompressibility. So I think we can just add it up.
I'm sure I think it's maybe dx minus d.
Yeah, dux plus duy, dvy is 0, right?
Oh, you're saying this is rewriting it.
Yeah. So I'm just rewriting it. So zero something. You can also replace that also. Right? So the other invariant is space and determinant. So maybe I think that's what you're trying to say. Okay. Yeah. Yeah. So any other question? Yeah. So we look at minimum values of vorticity and strain rate tensor, determinant of the strain tensor, and we asking the question, how is the distribution look like? And here I just point to you that it's a spatial field over which you take the minima. So at each instant you get one particular value. So we are looking at the distribution of these quantities, and just a few, just to show some typical flow structures. So this is for different values of these Reynolds numbers. So what we see is that so the plus point here is the minimum of the vorticity, and the circle here is the extreme value of the strain rate tensor. Determinant of the strain rate. It's always negative. This is the definition. So this circle is denoting this extreme values of this shear, and the plus signs are the extreme values of this vorticity. So if you have if a system is triggering centrifugal instabilities, there's usually around these plus points most. And if you are looking at this parametric excitation, it's usually around this this extreme strain rate tensor, where you have this excitation of this initial phase on top of this fluctuating background. And one can see that the minimum of the vorticity is usually typically found at the center of these vortices, and the strain rate tensor is at the edges of these vortices. Right? And so these are distributions that we find for the minimum of the vorticity and the determinant of the minimum of the determinant of the strain rate tensor. So this is for different values. Right? And then what I try to see is that, so my idea is to look at whether do we reach a Reynolds or viscosity independent shape of the distribution, so that which can be helpful for trying to model the growth rate intermittency. But what we see is that the distribution themselves do not form a do not reach a Reynolds independent shape, let alone the size. So we can on the width of these distributions, right? And we can rescale them and then rescale the things. And what we see is that even if we rescale the tails, the heads of the distribution do not fall on top of each other. So you see that it's a very non-trivial distribution. And these dashed lines are these extreme value distributions which are associated with these identical random variable distributions, right? This dumbbell, Fesci, and Weibull. So one can write down a general expression and try to fit these curves. See that they do a very bad job, right? So clearly correlations have some role to play. And the question is, can we get to try to understand? Let's say some models from statistical physics where people have looked at such kind of problems. And same thing goes with the determinant of the strain rate tensor. We also have the tails seems to have a better behavior there, but still seem to fit well. Is it better at high Reynolds? So at high Reynolds number, we also have this double kind of bizarre, and also for this particular problem, the for the determinant of strain rate tensor also, we do not fit with the standard distributions. Yes.
So in this case, when calculating, would this be assumptions related to the dissipation in this study?
Yeah. So that is also, it's related to 4 times minus 4 times mu times is determinant. I think it's related to the localized dissipation by the turbulent flow.
So in the 3D context, that dissipation is usually log normally distributed.
Yeah.
So is there something similar known for 2D problems?
So for 2D problems, there have been some bounds on these quantities. I do not know about the distributions of localized dissipation, but those are not extremes, spatial extremes. Yeah. So the general ones, I'm not. Maybe I have to go. I'm not aware of.
Because there are these stochastic.
For 3D turbulence, it is known to be log normal. For 2D, I'm not sure. There are some bounds where people have tried to show that the average is maybe a function of some log of the Reynolds number and stuff from the bounding literature. But the fitting, I do not know what they are fitted with. Yeah. Okay. So we have this distribution which are non-trivial, and they also depend on the dissipation coefficients. And for other values, so we also looked at the variations in terms of large-scale dissipation rate. So this is basically because of the confinement, we can also have this large-scale dissipation, and we observe similar kind of levels. So there's a strong dependence on the dissipation coefficients, and the question is, can we try to understand this? So instead of looking at the case with dissipation coefficient, I took the other limit, which is basically no dissipation case, which brought me to the truncated Euler equations. So truncated Euler equations are basically, so this is one set of equations where people have done a lot of statistical mechanics models to understand 2D turbulence. So these are effective in capturing large-scale dynamics of turbulence. So recently there have been quite a few articles on trying to understand, let's say, large-scale thermalization of fluid equilibrium in 3D turbulence, in wave turbulence, in also trying to understand certain type of modeling of these large-scale structures, of large-scale modes in 2D turbulence. So there have been some successes in trying to capture certain type of bifurcations using the truncated Euler equations. So I just have to warn you that this is not the same as, let's say, other statistical mechanics models of just the Euler's equations, where they preserve all the Casimir invariants, see all the moments of the vorticity. They try to preserve, and these lead to a slightly different model, statistical mechanics approach. But I will not be talking about that. So for those you can refer to these. I'm only looking at the case where you're looking at a system and you truncate beyond a particular wave number. So if you look at the system of equation, it only conserves the energy and the entropy. These are only two conserved quantities. The other Casimir invariants are not conserved. So the only because these are the only two conserved quantities, the control parameter is Kc, which is the some form of a wave number, which is related to the root of ratio of the entropy over the energy, right? So the equations can be written in terms of this stream function. It's basically an Navier-Stokes equation without forcing and dissipation, right? So there's no dissipation as such. There's no forcing as such. Right? So basically, you can borrow concepts from statistics and try to explain the behavior. So if you have large number of modes, you can use what is known as the canonical distribution, and one gets different forms of energy spectra, let's say. So there are some three different types of values of Kc as compared to the largest and the smallest wave numbers in the system. So these are just some equilibrium statistical mechanics solutions. And now the question is, Navier-Stokes equations gives extreme value distributions which are dependent on dissipation coefficient. What are the distributions of these contained order solutions? Because we do expect some kind of equilibrium to be set up, and there's no dissipation as such. So what do we observe? And so first, what we do is we just numerically integrate these equations for different values of Kc, right? And then look at the distribution of this vorticity and determinant of strain rate tensor at a particular point, at any random point in the flow. You can try to measure it, and they follow for large values of Kc. They follow a nice Gaussian or exponential behavior. So this is again comes back to the canonical ensemble. If you look at the canonical ensemble theory, you expect the distributions to be nice Gaussian distribution. The second quantity is scale like nice exponentials. But for very low values of Kc, this is when you have very few number of modes. You go into this condensate regime where you have very few interacting modes, and one has to go beyond the one has to use the microcanonical theory where you have only few coupled modes which are expected to be, and the canonical ensemble theory fails. Right? So this is why we do not expect very low values of Kc, but for large values of Kc, the canonical distribution seems to be working well. Right? The numerical solution. And at any point. So basically, it's like the n random variables. Each of the random variable has this Gaussian or the exponential distribution at any point in the flow. Now we are looking at the extremes over the whole domain, over the whole two-dimensional domain, and what we see is that for different values of Kc, we get distributions which are affected very nicely by the Gumbel distribution. Right? So here you have a system which is also a turbulence, quote unquote, turbulent system in a sense. These are solutions of the Euler's equation. So these are conservative system of equations. Yeah.
So when you were saying that these are the approaching a Gumbel distribution, the inherent assumption is the underlying vorticity or velocity gradients are Gaussian.
So if you want to approach a Gumbel, yes, it's not Gaussian. Some exponential, the tails should be exponential. Should fall as fast as an exponential.
Because they would not be Gaussian in the action.
So in an actual problem, they have power law tails. So you expect some kind of a Frechet or a variable distribution to be set up in these kind of situations. So if you have power law tails, right, then they go to, depending on what quantity you look at and the form of the distribution, you can go to either the Frechet or the variable distribution, which is also not what we are observing. Yeah. So I'll come to it. The role of correlations in a bit. So just to say that the truncate seems to extreme value statistics theorem where you expect a Gumbel distribution. The Gumbel distribution seems to be flat. So we can also do a exact solution like how I did for endpoints. How I showed as endpoints go to a Gumbel. You have to just basically repeat the whole calculation again, and you get the exact theoretical distribution, and which works for which is the canonical distribution. It's a canonical ensemble where all this Gaussian kind of statistics works well. Yes. Yeah. What has changed? Oh, it is just the vorticity and strain rate determinant tensor. Just the two quantities which corresponds to these two instabilities that I looked at. Yeah, so here it's just the maxima. So the minima actually. Sorry, there's a minima. So this is just a minima. So it's just a point in the whole space. But the actual flow has correlations. Yeah.
So the solution that you
So there are some correlations. Yeah, there are some. The effect of Navier-Stokes in determining which constants. Oh no, those are just three factors. There's some three factors which can be found for this different n number of modes. So there's a special correlation in the truncated order, but these correlations I just talk these are weakly correlated, where you can show that they still follow this couple, still can fall under this Fisher-Tippett lemma. Right? So that I'll show in a bit. So correlations do play a role, but for the moment, for the truncated order system equation, we do distributions for the standard extreme value statistics distribution. And we have, yes? Oh, the role of gamma. T also. I don't it's NT and gamma. Number of modes and stuff. So that are the same kind of distribution. How I derive the company distribution. Here's the two dimensions. So one has to do the same kind of derivation. So for the Navier-Stokes equation, we had a non-trivial distribution which was unknown extreme value distributions which were for uncorrelated variables. But for truncated order equations, even though they are correlated, they seem to be fitted very nicely with these known theorems. Right? So what is missing and what can we try to understand what's happening between the Navier-Stokes equation and the truncated order situation? So the structure of the equation is the same, though the dissipation and forcing are absent. So correlation. So you take the vorticity and determinant of the strain rate tensor, whichever quantity that you find. What one can look at is the power spectrum of that particular signal. So there's a time series, this construct the power spectrum. And what we see is that there's a strong correlation in our solution where you have a spectra which is some f to the power minus alpha. Right? Whereas for the truncated order solutions, if you in the regime of the canonical ensemble, we get distributions which are flat. The spectrum are flat, and then you have an exponential cutoff. Right? So the correlations behave like white noise up to a certain, and there's a fast decay of correlations. So there's a strong decay of correlation beyond a particular frequency, and below that particular frequency, the signal behaves like white noise. There is more stuff happening which are not going to details. But for a canonical distribution, it seems to have a correlation which is more or less flat. So with that observation, I turn to some of the other literature in extreme value statistics, which is just coming up slowly, which is about extremes of correlated random variables. So the extremes of correlated random variables are a lot more complicated. The sense that they have a like Fisher-Tippett code theorem. If I'm not pronouncing it well. So the distributions do not go to a known set of distributions. And what is we know that in certain systems, the signals are weakly correlated, meaning the power spectrum of the time series of one of these random variables, if it is following f to the power minus alpha, with alpha between 0 and 1, the alpha equal to 0 is flat line, which is a white noise power spectrum. So if you have a flat line power spectrum, noise, and if it is f to the power alpha minus alpha, where alpha goes from 0 to 1, we see weak correlations. So these weak correlations have also shown to fall under the standard distributions in certain situations. Whereas for strongly correlated signals, alpha greater than 1, what you observe is that the distributions start to deviate from the known distributions of Gumbel, Feshy, and Weigel distributions. Right? And also in spatially periodic, in spatio-temporal systems, like let's say KPZ or other forms of Gaussian distributions, randomized distribution models, what they observed is that the boundary conditions also change the form of the distribution. So it's very sensitive. The form of the exact distribution is very sensitive to boundary conditions and also the parameters of the system. So for alpha is greater than 1, there is no single non-trivial distribution for which the system goes. So with that, we kind of try to understand whenever you have a system which is highly correlated, so strong correlated systems, it's expected that they do not fall under the distributions or the set of known distributions. Whereas whenever you have weak correlations, right, f to the power minus alpha with alpha going from 0 to 1, this cases seems to follow a nice Gumbel distribution. So we also tried some simple noise models. So we have constructed some random noise signals with different power spectrum. So this is alpha equal to f to the power minus alpha with alpha like 0.2, 0.51, and so on. And what we observe is that when alpha is like 0 to 1, alpha is from 0 to 1, so there are some theoretical results also which I showed, which are present in these articles. But this should convince you that numerically also we find out that alpha less than 1 distribution of extreme seems to follow. But for very large values of alpha, the extreme value distributions seems to deviate strongly from the known distributions. Right? So here we also have this double E, which kind of reminds one of these distributions that you obtain for the Navier-Stokes turbulence. Right? So correlations play an important role in this extreme value distributions, especially the strong. Right? So finally, so just to stop where I am in understanding this problem. So spatiotemporal correlations. So strong temporal correlations, for example, if you're looking at spatial extremes, lead to non-trivial distributions, which are not in the known class of distributions. And there's a strong sensitivity to distribution parameters. And for the moment, at least, I do not know how to get to a single form of the distribution of the extreme. And the question remains whether are there any limiting distributions in the large Reynolds number domain. One can actually bound the moments of the distribution, but the form of the distribution itself seems to be very sensitive. And bounds are also not exact, so we do not know if there's an easy way to find out the extreme, the form of these extreme values. For the Euler equations, it seems to be directly easier to obtain these extreme value statistic distribution and explain it with the known distributions, except when the cases are closer to the microcanonical ensemble, where one has to do more work to get the actual distribution. So for the moment, I haven't linked it up yet with the anomalous exponents and other critical transitions, critical exponents that one can observe in these systems. So that is part of some ongoing. And it's also known that such kind of extreme statistics are also observed in more, let's say, systems related to Earth, some weather patterns, some one-hour of noise in a long time, this climate variability. There's a lot of interesting work where people have looked at such things, knowing the distributions of this long-time time series, the correlations of these long-time time series. Right? So, I don't know, but it seems to be interesting to see how much correlations play a role in these spatial extremes, which is something which people look at whenever you look at these heat waves across India and other places. So to conclude, extreme events can plausibly trigger these transitions from one form of turbulence to another, and the statistics of spatial extremes, at least for a 2D turbulent space, seems to have non-trivial behavior and linked with the strong temporal correlations in the system. For Hunter-Euler equations, on the other hand, we could kind of understand it, but yeah, for the 2D turbulence, it's still an open question, and it will be interesting to see what would be the possible consequence in other kind of systems. So these are some references and some collaborators. Thank you for your attention. For this last slide.
Any questions?
So Kannabiran to Navier-Stokes is a non-trivial. Yeah. Kannabiran PD has a different set of solutions which do not follow in the PD or Kannabiran is less than expensive. So you do not have this condensation and stuff. You only have the at the large scales, and then there's a cutoff even at which you have a residuality starting to develop. So you do not have this rich dynamics in 2D Kannabiran because of this negative temperature states here that you can get that you do not see in 3D Kannabiran. So I do not know about extremely distributions, spatial extremely distributions. 3D, it's a more complicated problem because like to do the numerics only it takes forever. But 2D only takes long. 3D, I'm expecting it to be like very difficult to converge the distributions.
Other questions?
Your conclusion, you said that the event trigger. My question is very basic. Do they actually trigger the transition, or are they just a signature that the transition?
Yeah, good question. Yeah, I don't know how you define trigger. So what is the cause? Yeah, for the
Maybe from the scientific point of view.
yeah. So I see what you mean. For the instability of this criteria, the Rayleigh criterion shows that whenever you have this vorticity patch which is less than 2 omega, and because the 2D turbulence itself is an oscillating state, whenever you get omega 2D less than minus 2 omega, one could actually exactly the growth rate with this omega minimum. Maybe there's a small time lag, but it correlates very well. Whereas for this mechanism, the parametric excitation, we kind of see a spatial and temporal correlations with the determinant field, the minima of that. But the thing is that I do not know a direct mechanism which links the minima of finite determinant to the growth of these. So this particular mechanism, the second mechanism, we do not have an let's say a nice Rayleigh criterion for this. The one way to understand this is to look at oscillating flows, but oscillating flows do not have such kind of minimum fluctuations as such, like a turbulence. So for the first case, I would say maybe they trigger. For second one, I would say just a signature. At least for the moment, I would say. Yes.
So from practical point of view, in your simulations, how do you identify when the transition has occurred?
Oh, so that is whenever you have whenever you have this growth rate, so it's a linear problem. So what you see is that whenever this growth rate of this so it goes like order like 10, 20 or 30 or 80 condition, you basically trigger the P action.
But you also look at the energy spectrum of the flow, the spectral slopes, and see if the transition has.
No, I don't know that. One could do maybe that, but I don't know.
So I had a question.
Yes,
You
please.
proposed the centrifugal instability
Yes.
and this parametric excitation for three-dimensional.
Yeah.
Aren't there other mechanisms? Or these are
For rotating flows, is it? Yeah, there's elliptic instabilities, but I'm still not understanding elliptic instabilities. So parametric excitation of inertial waves seems easier for me to understand than elliptic. The elliptic instabilities also trigger this three-dimensionalization. The problem is that it's weak electricity. Exact results by Stefan Ledizier. But I'm not sure for strong electricity, are there any exact results. So, for this, this parameter iteration base seems to be the scaling law and also has a nice example also. We do not know if there's an example of a strongly elliptical flow in a rotating system which could give such kind of scale. If there were there, we would maybe call it an elliptic institute. But for the moment, we prefer calling it parametric excitation of waves. Other than these three, I do not know.
And what would be the frequency of these inertial waves that are generated by?
So one has to form this triad. So basically, so there are many mechanisms. So there is this recent Basil also proposed quartetic instability, where if you excite two waves, forms a third wave, and three waves again to form a quartet, and then you get a two mode. Similarly, you can do the other way around. You start with few 2D modes and then get a 3D mode out of it, using again this quartet mechanism. So that is one way. And if you look at this problem from the context of locate theory, you can also form some triads where the underlying flow is modulated, and then create some triad, and that it obeys certain dispersion relation. But because of the underlying fluctuation oscillation, it's down. So there's a slight actual standard relation of the initial derivatives. I think so. If I remember correctly.
Any other questions? Thank you. He is